4-inch-long weaver ants have to make their nests themselves. They build them out of leaves. They turn the leaves into green chambers with floors, walls, and ceilings. The way they do it is with glue. First, some of the ants turn themselves into living safety pins, pulling the leaves together and holding them there. That's one team. Next come the weavers. They pick up larvae, their yet unformed little sisters, take them to the seams and use them like living shuttles, tiny glue guns. They stimulate them to secrete threads of sticky, web-like silk that holds the leaves together. Without any apparent supervision, the ants know exactly where to clamp the leaves and where to apply the silk. There are 500,000 ants in the colony, but they behave as though they were all part of a single mind, each one doing what's needed in the right way to build a complex of chambers and corridors out of living leaves. What kind of animals are these? What kind of intelligence? What is an ant? It's an insect, a social insect in the same group as the bees and wasps. A human weighs about 10 million times more than an individual ant. But since ants far outnumber people, all the ants in the world weigh about as much as all the people. But while there's only one species of human, there are thousands of different species of ant. Each one is a finely tuned specialist, exquisitely adapted to its own particular environmental niche. But all species of ant have the same basic body design. It's the best one for their miniature world, but it's a design that has kept them small. As insects, they have 6 legs and 3 body segments: head, thorax, and abdomen. And like all insects, ants wear their skeletons on the outside. This exoskeleton is a hard, waterproof armor that supports and protects. Ants breathe through their sides, through valves called spiracles. When they open, air rushes in, circulates through a network of tubes, and then rushes out again. Every cell gets its oxygen delivered direct. That's the internal air conditioning system. Ants also have a disinfecting system, a pair of metapleural glands that ooze antibiotic and keep both ant and colony free of germs. Only ants have this. Ants, in fact, are little chemical factories. A whole battery of glands produce chemical signals or pheromones that are the commands in ant communication. Ants send messages by laying a trail of these chemicals. And other ants pick them up with their antennae, which are covered in tiny sensory organs capable of reading the complex chemical messages. Then there are the eyes. They are made up of hundreds of small lenses that produce a mosaic image of the world. An ant's jaws or mandibles are its main tools. Molded from the hard exoskeleton, they come in every shape imaginable. Their size and design can tell us a lot about an ant's lifestyle. Mandibles are as important to an ant as our hands are to us. Depending on the species, they can serve as anything from scissors to forklifts to pliers. Really appreciating the variety among ants means looking at them close up. Professor Edward Wilson of Harvard University has been looking at ants for most of his life.
It's easy to think that all ants look alike. I mean, after all, we're looking at them from way up here, way down there, you know, like Godzilla looking at the inhabitants of New York City. But in fact, these little creatures are strikingly different from one another, one species to the next. One ant is typically as different from another kind of ant as a wolf is from a tiger or even a rhinoceros.
About 10,000 species of ants are known to science, and there are probably 10,000 more waiting to be discovered. The largest and most abundant group is the Pheidole ants. For the past 10 years, Professor Wilson has been studying, drawing, and describing the 625 species that make up this group. Over half are new species, and he is the first person to really see them in detail. Among them, he has discovered ants with weird and wonderful adaptations.
Let me give you an example. Two of the species that I'm describing right now have anatomical features which are just amazing. This is a species which has five, count them, five horns on the front of the head. It uses, I guess, as a battering device. It has two horns sticking out here, two horns sticking out there, and then a horn sticking like a nose out the middle. This was so unusual that I named it Pheidole mirabilis, the miracle Pheidole. Maybe I got carried away a bit with that, but I thought it was truly a wonderful one. Here's another one. This species has a plate-shaped head. I mean, just totally different from this other one. It has big bristles all around the head, but also conspicuously sticking out from around the mouth like a mustache. This one I decided to name Pheidole mistax. Mistax means mustache, the mustache Pheidole.
Get close enough to ants and they might almost be from another planet. They have evolved shapes and structures beyond human imagining. The one thing all ants have in common is society. These are wood ants. They're foragers, predators that go out, find food, and bring it back to the nest. Even though each ant is strong, capable of carrying twice her own body weight, a lot of the prey is just too big for one ant. In which case there's teamwork. It's not size, it's not speed, it's not even strength that makes ants what they are. It's this, the teamwork. Hundreds of thousands of cooperating insects spreading through the woodland like a huge digestive tract, pulling anything edible towards the gut of their nest. The nurse workers inside the nest don't go out to hunt for food. They stay in the darkness underground. Ants cannot eat solids. These foragers feed on the body fluids of their prey. Each takes what food it needs for itself. The rest is stored in a part of its gut called the social stomach. This food is for sharing. It is fed to the nurse workers, and it's done with a sort of a kiss. The ants lock jaws, and liquid is passed drop by drop from the feeder ant into the mouth of her hungry sister. One of the strengths of an ant colony is the individual ant's dispensability. Killing a colony by killing the workers is all but impossible. But one ant in the colony is absolutely vital, the queen. By using the sperm she stored when she mated, she's the mother of everyone, and everyone's future. An ant manufacturing machine at the head of a conveyor belt of eggs. Eggs are cared for by the nurse workers. These wood ant eggs stick together so that they can be carried easily as a bundle. The creature that emerges from an ant's egg looks nothing like an ant. What hatches out is the ant's larval form, the baby stage, an eating machine designed solely for growing. And as it grows, it sheds its skin to reveal a new skin underneath. 3 or 4 times this happens, until finally the eating stops and the larva prepares for the next stage of its life. This is the pupa, and developing inside the protective silk sleeping bag is a recognizable ant. All through this process, the nurse ants take care of their younger sisters, producing a steady stream of fresh, female, but sterile workers. But once a year, every year, they produce another kind of ant, ants with wings. Ants capable of sex. They're the males and fertile females that will spread the colony's inheritance far beyond this nest. They're what make the ants invincible. One day in July in northern Arizona, one colony of harvester ants is doing what all the harvester ant colonies in northern Arizona are doing today: launching. The once-a-year royal brood come above ground and begin to fly, and to find individuals from other colonies, and to mate. It's a scramble as the males battle to fertilize the young potential queens. And then, having done the only thing in life they were ever meant to do, the males die. All of them. Young queens die too, in great numbers. But some find just the right kind of fresh ground, dig in, and start laying the eggs that will give rise to new colonies. How did a system like this come to be? Once in the early days of the Earth, insects were the only land animals. They were also the only animals in the air. At least 100 million years before birds and bats appeared on the evolutionary scene, insects had wings. And one of those was a wasp, a solitary wasp living like many wasps that still exist today, stinging and leaving prey paralyzed for its offspring to eat. In time, some of these wasps started building their nests in clusters, probably to help deter predators. They were still essentially solitary, though, and their offspring left the nest as soon as they could fly. Then, millions of years later, appeared wasps whose offspring, daughters, didn't fly the nest. They grew up there and helped their mother raise more daughters. They became purely their mother's helpers, and didn't themselves reproduce. Over time, these wasps began to look more like ants. They lost their wings and evolved the disinfecting glands so that cramped underground living wasn't an invitation to disease. They hung on to their powerful wasp jaws and stings, though, and were among the fiercest predators around by the time the dinosaurs appeared. Ants not only saw a lot of individual dinosaurs come and go, they saw the end of the whole dinosaur dynasty. And ants have been ruling the world ever since. If the ability to communicate has made human society what it is, it's done the same for ant society. Professor Edward Wilson.
I'm often asked, do ants really communicate with one another? And the answer is, of course they do. Tiny animals that live in the ground almost have to communicate with chemicals. When you're that small, you're in the dark, a lot of the time in closed spaces, it's very difficult, obviously, to communicate by sight. It's difficult to evolve systems to allow you to communicate by sound. The ants have elaborated a chemical communication system, probably the most complex in the animal kingdom, and as close to what might be the kind of communication system we would find on another planet. In one of the early experiments, I succeeded in locating the gland at the end of the body, the abdomen, of the fire ant, a colony of which I have here, and extracting the material the ants use to lay odor trails that they follow.
When this substance is laid as an artificial trail, it speaks volumes to the ants. Although ants communicate using vision, vibration, and touch, at least 90% is chemical. 1 milligram of this chemical could lead a column of ants 3 times around the world. It is a sophisticated language of smell, an entire vocabulary of chemical signals and messages.
Ants detect smell in a way that is obvious when you think about it. And they do it with their feelers, the antennae, these appendages on the head that are constantly in motion, sweeping back and forth and up and down. Bristling, these are bristling with organs of smell that are very sophisticated in detecting wide ranges of minute traces of chemicals. They can sweep the antennae in and out of odor fields and know where to go according to where the smell is coming from. And they're very sophisticated in distinguishing large numbers of chemicals that way.
One use for the exquisite sense of smell is to tell insider from outsider. All the members of this weaver ant colony smell the same. Weaver ants from other colonies, even though they're the same species and look exactly the same, smell subtly different. What happens to an ant with that difference is not subtle. It doesn't matter what you look like, as long as you've got that membership smell. A fact a jumping spider dines out on. It has evolved the ability to mimic the smell of the weaver ant colony it lives with. Then it can roam freely among the ants, picking and choosing juicy meals. The soft, fat larvae are best. A weaver ant confronts what, as far as she's concerned, is one of her sisters. The ant's just doing her job, carrying a larva from one place to another. And here's a sister ant that's bigger and stronger than it ought to be, and doing something it really ought not to be doing. But the smell is kosher, and while there's cause for confusion, there's none for alarm. Despite the occasional counterfeiter, though, smell is overwhelmingly useful to an ant. Except here. It's no use at all in the eastern Sahara, where delicate odors are instantly burnt up by the sun. But that doesn't stop these ants, called cataglyphus, from foraging. Nothing stops them. Not temperatures of 130 degrees, and not burning sand. The ants scavenge for creatures that have succumbed to heat exhaustion. When food is found, the ant must return home as quickly as possible to avoid a similar death. Getting lost could be lethal. But how do they find their way around? That's what this team of Zurich University students, working under Professor Rüdiger Wehner, is trying to find out. It may look as if they're getting ready for a game of giant chess, but it's really like giant graph paper. And it's used to follow and record the desert ants as they search for food. It has to be done at the hottest time of day, because that's the only time the ants come out. What it shows is that when an ant is looking for food, it meanders and stops a great deal, but when it finds something, it heads home in a straight line. So how does it know where home is? Remember, there's no chemical trail to remind it of the direction. Professor Wehner has been studying cataglyphus ants for 20 years, developing his theory that it's something to do with the light. What's more, it's something to do with the sky. Professor Wehner's trolley-wheeled orange filter changes the way the ant sees the sky.
What I'm doing here is to investigate how the ants find their direction home. For this, they have to use a compass, much as we use a magnetic compass to find our direction home. But the ants, they use a skylight compass, a compass based on a pattern in the sky that is invisible to us. If you look up to the sky, for you it's uniformly blue. But the ant sees a pattern, a structure in the sky. And this structure is called, physically, the pattern of polarized light.
Using their skylight navigation system, the ants are able to determine accurately all the points of the compass. And as the ants run across the hot sand, they stop regularly to take note of the changing patterns in the sky. But just how much sky, Professor Wehner wondered, does the ant need to see?
With this here orange filter we see mounted on this trolley, we can destroy this pattern for the ant. But we would then leave a tiny opening in this filter, so that the animal can see a small glimpse of this whole pattern. And we are amazed to see that the animals are still oriented, even if the information is restricted to such a small area of the sky.
But is the sky all the ants use? This experiment is to show that the ants pinpoint the exact location of their nest entrance using visual landmarks on the ground. These are very obvious landmarks, something for an ant to remember. The ant needs to find its way home to its nest. And followed by its student minder, it zigs and zags its way across the desert as it heads for home. It has a memory of what its nest entrance looks like, a visual snapshot stored in its head. It constantly searches to match this image with what it actually sees. And when the match is made, home cannot be far away. Not all ants are predators or scavengers. These are the leafcutter ants of Central and South America, and they're a farming community, and they were farming 50 million years before we ever were. They don't farm the plants whose leaves they're actually cutting. No, these are wild plants growing within a 200-yard radius of the ant's nest. The ants cut out sections of leaves and carry them like sails to the nest. There, the leaves are handed over to other ants, which clean them and cut them into smaller pieces. They then weed it, harvest it, and feed it to the other ants. It's a complicated operation, and it takes specialists to run it. There is a definite division of labor. The tiniest ants spend their whole lives in the small, dark chambers planting the fungus. Next up are the mulchers. Then the chewers. The largest workers are the porters, the outdoor ants that cut the leaves and carry them. And then the soldiers, which don't labor but simply stand by to defend the nest. And the very biggest is the source of all the ants, the mother of the colony, the queen. Each individual is created for its role, specialists on an assembly line that is supremely efficient. Many plants make poisons. They do it to protect themselves. But because the leafcutter's fungus is able to neutralize most plant poisons, the ants themselves will take almost anything back to the nest. It's a big advantage. They can cut whatever's handy. But there's a failsafe. Just in case some plant makes a poison that the fungus can't handle, the porters are always careful to stay to separate pathways, to deliver to separate entrances and separate farmyards. So if something deadly is introduced to the nest, it only ever affects part of the colony. And if part of the colony dies, it doesn't matter. The colony just expands in another direction. Another potential problem is wild fungi. The ants have created perfect conditions for their own domesticated variety. To keep a hardy wild species from invading and taking over, they apply weed killer. It comes from the metapleural glands, the same glands that all ants use to suppress bacteria. Humans fight bacteria too, but the bacteria mutate to resist human antibiotics almost as fast as scientists can find new ones. Can ants help? Professor Andrew Beattie of Australia's Macquarie University thinks so.
We started by asking a very simple but very powerful question, and that is, where would you expect antibiotics to have evolved? And one answer is amongst animals that, like us, like human beings, have evolved to live in highly organized societies where contagious disease takes hold very easily and very quickly. And of course that applies equally to people and to ants. One of the big problems about ants, of course, is that most of them are very tiny, and so we were looking for the biggest possible ones to start our research, and the Australian bull ant is one of the biggest in the world.
This inch-long ant also has very large jaws and a very nasty sting, so the researchers first had to devise a way to keep everybody out of trouble. A wild bull ant is virtually germ-free. The antibiotic nature of the liquid that oozes from its metapleural glands keeps it free of bacteria and fungal infections, and much cleaner than human skin. Although the bull ant is a big ant, the opening to the metapleural gland is very small. A microscope, a steady hand, and a microfine glass pipette are what's needed to draw off the liquid. Once enough is collected, the ant is returned unharmed, if a little dazed, to her colony. In the lab, the secretion is tested on a range of bugs that cause diseases and infections in humans. It's been shown to kill bacteria that are resistant to many common antibiotics. In a world where new antibiotics are hard to find, ants would seem to have a promising future.
Recently, word has got around about our research, and I had a phone call from an Aboriginal woman who told a fascinating story of growing up in the bush. When she was a child, if she got a cut or a gash, her mother would take a piece of clean cloth and throw it onto a bull ant's nest and stir it around and get them really angry. Then, when the cloth was covered in these enraged animals, she would take it off with a stick and shake them off, and then she would use the cloth to bind the wound. And this clearly suggests that she understood the healing properties of bull ants. And from this point of view, I feel that our discovery is in fact really a rediscovery.
The native Australians first came to this continent about 40,000 years ago. Some say 80,000. They know the land. They know, for instance, that ants collecting nectar from mulga trees have a secret. It's a secret that gets the ants through the hard, dry times, which is most of the time in the vast interior of Australia. They store the mulga nectar in underground pots, living pots. They're ants whose existence serves one purpose: to receive nectar from their sisters and fill their abdomens with it. They don't drink much of it themselves. They just keep it and regurgitate it when it's needed, hanging from the roof of their underground nest like subterranean grapevines. And the native Australians know how to harvest them. The women look for the telltale signs taught to them by their grandmothers, and when they see them on the surface, they dig. It's hard work. The ground's dry, and the storage ants, which are called honeypot ants, are about 4 feet down. It takes hours sometimes, and great skill. The digger has to dig down beside the storage chamber, not through it, which would destroy it. And the honeypots have to be prized out gently so that they don't burst. Careful handling ensures few honey sacs are broken. In the end, the energy spent digging out the ants is probably greater than the energy gained from eating them. But this is a place where natural sugar is rarer than uranium, and wherever it is you happen to live, you need a treat sometimes. An English woodland. It's not the warmest place in the world, and the wood ants that live here have to build their nests with that in mind. As insects, ants are cold-blooded animals, which really means that they're the same temperature as the air around them. But wood ants have ways of bending that rule. They use architecture, thatching, lots of thatching, pine needles, leaf stems, and twigs that to them are the size of tree trunks. They pile the stuff up in a mound about 3 feet high and shaped so that it absorbs maximum warmth from the sun. But the ants have a way of raising the temperature inside the mound even further. When the sun's shining, the ants come outside and sunbathe. They soak up the heat and take it down inside the nest with them, using their bodies as little radiators. The wood ants turn a stack of twigs into a world with its own independent climate. There are even internal variations, with the warmest parts in the center. One reason the heat is necessary is that the delicate larvae have to be kept at a more or less constant 74 degrees. And as the heat in the nest goes up and down and shifts throughout the mound, the nurse ants, carrying the larvae, have to keep chasing that perfect temperature from chamber to chamber. What wood ants have done for themselves is to open up natural barriers. Their heating system means that they can live in parts of the world that, by rights, are too cold for ants. Another kind of forest, a tropical one in Australia. And hanging high in the canopy and made of glued together leaves, a nest of rattle ants. Inside, it looks like ant business as usual. If it weren't for the green floor, these could be any ants underground. Except, what are these big things? They're not larvae, at least not of ants. This is a caterpillar of the small oak blue butterfly, and it has a little nozzle on its back. From it comes a nourishing liquid called honeydew, which the ants collect like dairy farmers. By being useful to the ants, the caterpillars gain their protection. And they're useful for more than just their honeydew. Up on the roof, danger. The caterpillar seems to sense the spider. It signals on the leaf floor. The ants become agitated and prepare for battle, flexing themselves and getting their weapons ready. They peek out to see what the actual danger is. A spider. And then it's all mandibles on deck. They spray at it and drum the leaf, making the sound that gives rattle ants their name. Exit spider. There seems to be a thing between ants and caterpillars. The two are often found together. Dr. Phil DeVries of the University of Oregon has studied caterpillar-ant relationships all over the world.
The interesting thing about caterpillar-ant associations is they're quite literally everywhere in the world. And the butterfly caterpillars associate with ants to gain protection against predators, mainly insect predators. The caterpillars produce a food secretion to the ants, and this is the way they pay for their protection. It's like if you had a bodyguard, you have to pay the bodyguard to protect you. But the problem here is that if you're a caterpillar and you're producing a reward, what stops the ant from simply going, "Thank you very much," and turning around and going back to the nest? One of the more fascinating things that the caterpillars use to keep ants with them is that they produce a call. So you have singing caterpillars, and you have caterpillars singing to ants, and the sounds that they make are attractive to the ants.
What's strange about these sounds is that we cannot hear them. The calls the caterpillar makes do not travel as sound through the air, but as vibrations through the solid plant stem. The ants detect the vibrations using unique sensors on their legs. We need the help of a special microphone.
So, for example, this caterpillar, if we pick it up and we put it on this membrane that I have here, we hear nothing now. But if you use the very sensitive microphone, and as you'll hear, that produces a call. You can quite easily hear the caterpillar singing. Now, think about it. How many caterpillar calls have you heard? And what's neat is that every morning there's a dawn chorus of caterpillar calls that nobody hears.
It was while working in Panama on one particular group of butterflies that Phil DeVries first discovered how the caterpillars made their calls. He noticed that they had two rod-like appendages right above their head, stuck into their collar. Called vibratory papillae, these beat up and down on top of the head, and the head itself moves in and out. The papillae have pronounced rings and move over small bumps like guitar picks on the caterpillar's head.
I was reminded immediately of this. which is the South American salsa instrument called the güiro. There's deep grooves in the appendage, like the güiro, and simply that runs up and down across the head, producing a call. The caterpillars, with their calls, are effectively deceiving the ants because the caterpillars are talking in ant language. And if there are caterpillars on the moon that associate with ants, I'll bet they make calls too.
So the caterpillars talk to the ants, and the ants protect them and milk them. It's a good deal for both. Except that somehow the relationship between this caterpillar and the rattle ants has developed a strange twist. The caterpillar eats the ant's larvae. Most caterpillars eat leaves, and in a way it's lucky this one doesn't, or the ants would literally be out of house and home. But it does seem strange when what amounts to your cow dines on your children. It's been going on for millions of years, though, and both species have obviously survived. Australian weaver ants, and a normally fearsome spider that has wandered onto the wrong leaf. The ants don't care what reputation a creature has. If it comes too close to their nest, it's simple cause and result. They attack, and clinging to the leaf with special claws on their feet, pin their victim down, carve it up, and take it back to their nest. What enables ants to behave this way in perfect cooperation is that they all have exactly the same instinctive response to the same set of events. They're programmed. It's their strength, but also sometimes their weakness. And this little Thomasid spider, which looks like nothing compared to the monster spider the ants have just dismantled, knows how to hack into the ants' program. It not only smells like a weaver ant, it looks something like one too. The ants tolerate its presence. This spider does not spin a web. It has other ways of hunting. The lethal bite. And the patient wait. Ants, with their social organization, can be the most effective predators on Earth, but cross their wires and they're pushovers. Some kinds of ants, though, are never pushovers. No predator would take on these ants. Army ants. There are about 500,000 in this bivouac. The whole colony, including, somewhere in the middle, the queen. On the march. These ants can barely see. Blindly following chemical trails laid down by their nestmates, they take everything edible in their path. And there's very little anything else can do about it. You could say they're a mob, but more organized and more single-minded. To the wasps watching the pillage of their nest, this colony might be a huge amoeba with tendrils spreading through the forest. But more than an amoeba too, because each of these ants has a brain. Not a very big brain, but all of their processing power added together gives them a kind of collective intelligence. Is that what ants are? A big, many-legged brain? Professor Nigel Franks.
I think that what most impresses people about ants is just how incredibly well organized they are at the collective level, at the colony level, and how incredibly determined they seem to be. Because people think that they're so well organized, they think that they must be organized as we are, but even more so. In other words, that they must have really a rigid hierarchical control with a key person deciding what everyone ought to do and having a sort of chain of command, telling the workers what they ought to be doing.
But most ants, it seems, are organized from the bottom up rather than the top down. No one ant is in control. The individuals organize themselves. It's almost like anarchy that works. It's a formidable evolutionary strategy.
I think what is interesting about army ants is that they're perhaps more likely to start experimenting upon me than I was to start experimenting upon them. So what I chose to do was to look at a very contrasting species. And Leptothorax are, I think, one of the absolutely ideal species to keep in the lab. We've got them nesting between glass plates in a very small cavity here. And the beauty of this is that we can watch all the ants all the time and really study their behavior in tremendous detail. And they're just really very, very nice ants. I mean, to get a feeling for the scale of them, I often imagine that it would be nice to have a colony inside your watch. If you took all the gubbins out, a colony could very easily fit into a space like that. What we're interested in with this experiment is how a colony finds a new nest and how it does all the operations to move into it. So what we do is simply tip a colony out onto this platform where there are no nesting opportunities at all, and one scout will find the bridge and walk across, and we'll actually walk around inside this beautiful ideal home on this side, and if it's happy it will go back to all its nestmates. And what it will do is quite extraordinary. It will actually pick up a single worker and carry it all the way back over the bridge, and then they both look round the new home, and if they're both happy, the whole thing snowballs until we've got this enormous stream of traffic from the old colony to the new one.
When the whole colony is safe inside the new nest, some of the workers begin building a protective wall across the entrance. Grains of sand become huge boulders in the jaws of these tiny ants.
Each ant indulges in what I call bulldozing behavior, where they absolutely thrust the building block into the wall and trundle it in. Essentially, they've built a very beautiful retaining wall, and they put it in exactly the right place. So even though this might seem a very odd thing for a scientist to look at, we're looking at how individual behaviors scale up to something that is far more impressive. And actually, I think that that's a really major principle throughout the whole of biology, looking at how simplicity at one level generates more sophistication at a higher level.
Ants are supremely organized, yet there's no hierarchy, no one ant in command. Their organization is unique. Ants are always at the grassroots of the problem they're trying to solve. Each ant is part of the decision-making process. It's the way they've been solving problems for 100 million years. Ants really are the ultimate millennium bugs.